having some problem with the canvas. I'm exceeding the storage on Canvas, so all my videos now will be on my YouTube channel. All right, so after midterm 1, we moved on to talk about chemical bonds. So this is the structure of our entire course, right? So this course is called Chemical Structures. What we did is we start from the very simple particles. We're asking us the fundamental question, what is the nature of a basic particle? By say particle, what is the nature of an electron from a physicist's point of view? That's why we introduce quantum mechanics and introducing what is the nature of particle. In that end, we finished talking about basic quantum mechanics theory for midterm 1, and we finished talking about hydrogen atom, which is the only atom we can solve its Schrödinger wave function in full with an analytical solution. And then we moved on to talk about multi-electron atoms, talking about the electron configuration of those multi-electron atoms, the shell model, and also the effective core potential. After midterm 1, we start to talk about bonding theory. So the fundamental question between midterm 1 and midterm 2 is, what is a chemical bond? For that regard, we introduced 3 different theories. One of them is classical, and 2 of them are quantum bonding theory. For the classical bonding theory, what we're talking about is electrons are imagined to be pure negatively charged particles, and nuclei are pure positively charged particles. And those shared electron pair in between the atoms will glue the nuclei together. So that's the foundation of the classical bonding theory. We're just talking about electrostatic attraction and repulsion between electrons and nuclei. It's not technically speaking correct, but the classical bonding theory is very useful for chemists. For that regard, we went over the Lewis-Dot diagram, so how you can figure out the connectivity between different atoms in a given molecule. Also, we talk about the VSEPR, the valence shell electron repulsion theory. That gives you an idea about the molecular geometry, or in short, what your molecule will look like if you know the position and also the number of atoms bonded to a specific center atom. So those 2 topics are from our classical bonding theory, all right? Lewis-Dot diagram, VSEPR, and also like polarity, dipole moment. These are all in the classical bonding theory domain. So that's one thing. With that in hand, we then move on to talk about quantum mechanics bonding theory. So for quantum mechanics bonding theory, what we're always talking about is molecular orbital. So the idea of molecular orbital is the same as the atomic orbital. What we're doing here is we have a wave function that describes and tells you everything you want to know about the electron that's being shared in your atom, in your molecule. The difference here is in the bonding theory, now you have multiple nuclei. So we're always talking about the molecular orbital. It's equivalent of the atomic orbital we talk about for a specific atom. All right, so both molecular orbital and atomic orbitals, they are wave functions. They're Schrödinger wave functions that give you the information about electron density, where your electrons are. However, as we probably already know, the Schrödinger equation is complicated, and you can't really solve it by hand for anything that's more complicated than just one electron. Even the hydrogen atom itself is hard. So for chemical bonding theory, we came up with approximations. So there are 2 different approximations we use. The first one is called linear combination of atomic orbitals, or LCAO-MO molecular orbitals. So that's shown here. What we're doing is we're talking about the MO as a linear combination of atomic orbital A plus minus atomic orbital B. All right, so that plus minus tells you if you start from 2 atomic orbitals, you end up with a pair of bonding and anti-bonding molecular orbitals. So you create molecular orbitals by linear combination of your atomic orbitals. And because your atomic orbital is a wave function, when they interfere with each other, when they add up to each other, it can add either constructively to form a bonding MO or destructively to form an anti-bonding MO. So that's the foundation of the LCAO-MO theory, right? And we're trying to use the linear combination of atomic orbitals to give you an estimate on what that molecular orbital looks like. So that's the LCAO-MO theory. So for that, we can use the LCAO-MO theory to draw out the energy correlation diagram that gives you information about chemical bonds. So LCAO-MO theory is very useful. It gives you those energy levels for your bonding and anti-bonding MOs. You can deduct information like bond order or like the electron configuration for your molecule by just reading that correlation diagram you created. So that's the LCAO-MO diagram. For the valence bond theory, that's our second quantum mechanics bonding theory. So in valence bond theory, what we're talking about is now instead of taking the linear combination of atomic orbitals, you're taking the products of the atomic orbitals to give you an estimation on what your molecular orbital looks like. So the LCAO-MO is linear combination. You're just adding them together. The valence bond theory is a little bit more complicated. It gives you information about your wave function by taking the product of your atomic orbitals. So again, we have some constants, and then we have phi A1 products, phi B2 plus phi A2, phi B1. All right, so in the valence bond theory, we're having the product of your atomic orbitals. The reason we have two of them here is now you don't know which electron comes from which atomic orbitals. They're indistinguishable from each other. That's why we have two terms in your valence bond molecular orbitals. So just as a quick summary on what we have done between midterm 1 and midterm 2, we have three different bonding theory. You have classical bonding theory, Lewis-Dot diagram, valency, VSE-PR theory, and everything. It's not technically speaking correct, it's very useful, and you will need it in organic chemistry. And then we have two different bonding theory, the LCAO-MO theory. We're talking about the linear combination of atomic orbitals to give you an approximated molecular orbital. Valence bond theory, we're taking the product of atomic orbitals to give you an estimation on your electron density. For the valence bond theory, last lecture, we also talked about hybridization. It's just using the valence bond theory itself sometimes does not rationalize chemical bonds in multi-atom molecules like CH4 or BH3. So that's why we introduced the idea of hybridization. Do we have any questions for the general review on what we discussed in these past months? Yes?
For the LCAO-MO, you get like an antibonding and bonding because of the plus and minus, right?
Yes.
For the VB, why don't you get like a plus and minus?
So for the VB theory, we in this class, we'll just talk about the plus. There's also a possibility of a minus that gives you a non-symmetric valence bond molecular orbital. It's more complicated, and we will not talk about it in this lecture. Next question. All right, so we'll come back to more questions later on, but I want to spend some time in catching up where we left over. The first thing we left over is the molecular correlation diagram of HF. So this will not be on your midterm 2, but it might be on your final. Quick reminder, we're talking about electron correlation diagram, right? We're trying to use the LCAO-MO to describe the chemical bond in your HF. So to get started, here are the procedure we would like to use. The first one is write out the electron configuration of fluorine and hydrogen. So hydrogen is easy. That's just 1s1. And fluorine here, that's helium, 2s2, 2p5. So in this case, what we have, the valence atomic orbitals that we need to include in our correlation diagram is the 1s1 for hydrogen and the 2s2, 2p5 for the fluorine. So I'm just going to draw it on the document camera here if you want to draw it with me. This one is more vertical, I think it works better. Again, what we have is, let's just write the coordinates as the energy. On the left, let's write hydrogen and fluoride. Hydrogen, the electron configuration, that's 1s2. Fluoride, that's 1s2, 2s2, 2p5. This one is our core, we're not going to show it. And then if you think about it, I want you to, for these type of examples, you might want to think a little bit harder in where to put these atomic orbitals. So on your y-axis, that is energy, right? So in our previous discussion, we know that energy equals to negative v squared, f squared, if we have multi-electron, over n squared. So you can calculate, or you can estimate the energy level for these atomic orbitals by just calculating them. So for hydrogen, this calculation is quite straightforward. 1s equals to negative 1 squared over 1 squared, which is negative 1. So our energy is in Rydberg. All right, so I'm just going to put that. Can you all see it? All right? Okay. So I'm just going to put my 1s here. And that's my negative 1. For fluorine, that's slightly more complicated. We can't calculate it for 2p, but we know 2p is higher than our 2s. But we can calculate the energy for our 2s here. So for 2s equals to negative f squared over n squared. So for 2s, what we have is f equals to 9 minus 2. So 9, that's the atomic number of fluorine. 2, that's coming from the 2 inner shell electron, minus 1/2 of the same shell electron minus itself. So here is 1/2 of 7 minus 1 times 6. All right, that's just how you calculate the effective core potential. And you end up to be 7 minus 3 to be about 4. And then n equals to 2, you can estimate your energy of 2s to be negative 4 squared over 2 squared. Or about negative 4. Did I do that calculation right? All right, so this is just calculating effective core potential and translate that calculation into the energy level. And since we're plotting hydrogen and fluorine on the same energy plot, right? So if this one is negative 1, then my 2s of fluorine must be down here. This is negative 4. That's what we estimated by doing that energy calculation. And at the same time, we know that the 2p are higher in energy, slightly higher in energy compared to 2s. All right, so let me just leave it here and go back to what we have. So 1s of hydrogen and 2p5 of fluorine. So these are our interacting atomic orbitals. These are our valence atomic orbitals we need to put on our correlation diagram here. All right, so that's preparing the canvas. Next step, draw the energy level diagram of your atomic orbitals. Okay, I already did. And then create the LCAO MOs. So here are some of the rules you might want to keep in mind. First of all, the number of atomic molecular orbitals created must equal to the number of atomic orbitals. And then each pair of the atomic orbitals of the similar energy Let me highlight that. Will interact to form one pair of bonding and anti-bonding MOs. Everything that's not interacting is going to stay where they are. What that means on this figure, use a different color for your molecular orbital, is atomic orbitals of the similar energy will interact. So that means the 2p of your fluorine and the 1s of your hydrogen are closer in energy to interact with each other. What that means is we'll have a pair, one of the 2p interacting with the 1s of the fluorine, 1s of the hydrogen to create a pair of bonding and anti-bonding MO. All right, so this pair comes from the 1s of hydrogen and one of the 2p of the fluorine. Because we always define the bonding axis or HF axis to be our z-axis, it's always the 2pz interacting with your 1s of hydrogen here. So here, what we have is our sigma and sigma star. If we were to draw these molecular orbitals, what we're having is a hydrogen, that's our s orbital. It's the s orbital of hydrogen interacting with the pz of fluorine. So that's our bonding molecular orbital. What we're doing essentially is very straightforward, right? You're just imagining that's our pz atomic orbital, and that's our hydrogen. You're just putting them in close proximity and they interact with each other in a constructive fashion. Or they can interact via a destructive fashion, and that creates a node. And that's why it is a sigma star anti-bonding molecular orbital. So we start from two atomic orbital, the 1s of hydrogen, 2pz of fluorine. We end up with a pair of bonding and anti-bonding MO. So that's the first step. Next step, what happened to the rest of the atomic orbitals on your fluorine? Your hydrogen doesn't have any other atomic orbitals fluorine can interact with. So the result here is whatever left over will become our non-bonding molecular orbitals. It comes from atomic orbitals of fluorine alone. It doesn't interact with your hydrogen. So these are called non-bonding molecular orbitals. So these should be of the same energy. I don't have a ruler, but it's just the same energy. And we call it sigma non-bonding, pi x non-bonding, and pi y non-bonding. All right, so these non-bonding atomic orbitals, just coming, molecular orbitals, coming from the fluorine atomic orbitals alone. So now we're ready to assign electrons, right? So this calls the end of drawing the molecular orbitals. And now we're just putting the electrons in there. So I'm using, again, a different color. Oh. For hydrogen, we have one electron in there. For fluorine, we have two in the 2s, 1, 2, 3, 4, 5. 5 in your 2p. So in total, what we have is 1, 2, 3, 4, 5, 6, 7, 8 electrons. And we're putting these electrons into your molecular orbital. And then you do it by putting the electrons in the lower lying molecular orbitals. So likewise, these sigma non-bonding just purely coming from the 2s of your fluorine. And then the sigma here get filled up next. And then here the pi non-bonding. So that finishes the preparation of a correlation diagram, a MO correlation diagram. And imagine what these MOs will look like, right? So for example, the pi y non-bonding, we have the hydrogen, that's just a hydrogen. It doesn't have any atomic orbital to interact with. And here, fluorine just have its y atomic orbitals. It's not interacting, it's non-bonding, but the orbital is still there. It's not pointing toward each other or anything. It's just, you need to have that molecular orbital, even if it's just coming from your atomic orbital. And at the very end, as a sanity check, you can check the number of electrons in your MO correlation diagram and make sure the total number of electrons matches up. We don't create or destroy electron from void. Right? Whatever, we start from 8 total electrons in hydrogen and fluorine atom, we end up with total of 8 electrons in your HF molecule. All right. How are we doing here? Okay. So if we don't have, yes.
Sorry, I have a quick question. So the diagrams over there, are they required when you draw these molecular orbital diagrams? You see like
the molecular orbitals?
No, you see that there's like a diagram at the top next to the sigma star that says like no. Yeah.
This one?
Yeah, it is required when you.
Right, so these are the sketches of molecular orbitals. So they're not required, but I might ask you to draw the molecular orbitals of, say, a sigma star or a pi non-bonding X or a pi bond or something like that. Yes?
What do we do with the FP non-bonded? Like the pi y non-bonding, what do you do with the atoms?
Yeah, so what's the question here?
Why would this be in the bottom and not in the top?
So for the non-bonding molecular orbitals, they're called non-bonding. They're not interacting with any of the chemical bond. The energy level just stays where they are. The energy level here, these non-bonding MO has the same energy level of your px and py atomic orbital. The sigma non-bonding has the same energy level as your 2s atomic orbital. The atomic orbital is not involved in the chemical bond. It stays where it begins. Only when the atomic orbitals are interacting with each other, you get that pair of bonding, anti-bonding molecular orbitals. All right. Yes?
So there's no anti-bonding?
No, there doesn't exist. So we don't characterize a non-bonding molecular orbital to be bonding or anti-bonding. It's non-bonding. It's a third type. So for molecular orbitals, you have bonding, anti-bonding, and non-bonding. Non-bonding just means that molecular orbital is not involved in the chemical bonds. All right. If there's no more question, we're ready to move on to talk about hybridization more. All right. So you can, again, for these correlation diagrams, just practice a little bit more on them. You'll thank me for that. You can almost for sure to know there is a correlation diagram problem on your lecture. Okay. So hybridization and multiple bonds. We discussed hybridization and valence bonding theory at the end of our last lecture. Remember what we're doing here is depending on the steric number, you can have a mix of your s and p orbital, and now you have singly occupied, hybridized atomic orbitals, ready to undergo chemical bonds with another molecule, with another atom. So what we're showing here are some examples of how to use hybridization and valence bond theory to describe some of the very fundamental things you need in organic chemistry or multiple bonds. So we'll start from the all single bond case, an ethane, which is a straightforward example. you might be asked to draw the chemical bond using valence bond theory and hybridization of ethane. So here is a quick procedure in how you want to do it. First step, in ethane, you can draw its Lewis dot diagram, or in this case, what we have is just a CH3 bonded to another CH3. Or if you may, draw it out with your VSEPR information. Each carbon here has single bonds to 4 different other atoms. And if you count for the steric number at both carbon, steric number always equals to 4. Or here, the distance, the bond angle is about 109.5 degrees. That's a quick review on VSEPR. With that in hand, you can calculate the hybridization on your carbon center. So steric number equals to 4. That tells you all carbon are sp3 hybridized. So what that means is, if you look at it, you start from 1 to s and 3 to p atomic orbitals. And this hybridization makes 4 sp3. Hybridized atomic orbitals. What does this sp3 mean? This means the sp3, each sp3 hybridized, the sp3 hybridized atomic orbitals coming from 1 s atomic orbital and 3 p atomic orbitals. So in total, we have 4 sp3 hybridized atomic orbitals. And then it becomes straightforward to sketch your chemical bonds. Because we know each carbon have 4 sp3 hybridized atomic orbitals, it is making 4 single bonds. So what we're going to draw here is we'll just draw the carbon, and then the hydrogens around. Before we draw the hydrogen, let's just look at the first carbon-carbon bond. So that's our first hybridized atomic orbitals interacting with each other. So that's our sigma bond between the carbon-carbon center. So it's an interaction with the sp3 and sp3 hybridized atomic orbitals. And then you can have interaction with the hydrogen atoms. So what we're drawing here is each carbon have 4 sp3 hybridized atomic orbitals. What I'm drawing here are the sp3 hybridized atomic orbitals. And at the end, you have the hydrogen 1s. Little tired, didn't draw it 6 times. I'm just going to copy paste it down. All right, so if you were asked to label what's the nature of that CH bond, what we have here is a sigma bond between sp3 of carbon and 1s of hydrogen. We're using the valence bond theory, so we don't need to add shading in our chemical bonds here, because in valence bond theory, we're taking the product of these atomic orbitals. Or if we're talking about the sigma bond here, right? If you're writing the valence bond electron, what we're having, the 5VB equals to some constant times sp3 of C1 with electron 1 times sp3 of C2 with electron 2 plus sp3 of C1 with electron 2, sp3 of C2 with electron 1. We still have 2 electrons in that chemical bond, but we don't know where that electron is, or with which atomic orbital that electron is. Yes? So that's actually the little tail of your hybridized atomic orbitals. So remember, we created hybridized atomic orbitals by overlying a p orbital with a s orbital. So if you have a p orbital looking like this and a s atomic orbital looking like this, after overlay these atomic orbitals, you end up with a bigger lobe here and a small lobe here. So that small lobe just coming from that hybridized atomic orbitals. You can also not showing those small lobes, it's also okay. You just need to know they actually exist in the hybridized atomic orbitals. All right, so how are we dealing with this all single bond example?
Are the coefficients multiplied by this sp3?
Coefficient is just the one bulk coefficient at the outside of that parenthesis. So it's multiplied to everything.
So what's the term to the left of sp3?
This one?
No.
That's the parenthesis.
The second, like inside the parentheses.
Yeah, these are the parentheses. Which term you're talking about?
The second sp3 is the very left of it.
This one?
No. To the left of sp3.
2 electron of sp3.
No, never mind.
We'll talk after class. Okay, yes.
Is this the equation for specifically between the two C's?
Right, so this equation is for the interaction between the two sp3 hybridized atomic orbitals. You can likely write that for this interaction between the 1s of hydrogen and the sp3 of carbon. We can write that together. The Vb will equal to some constant. I'll use the parenthesis literally here. sp3 of carbon with electron 1, s of hydrogen with electron 2, plus sp3 of carbon with electron 2, s with electron 1. So it's the same idea, right? You're just identifying which atomic orbital is involved. The atomic orbital involved can be a normal one, like an s orbital, or a hybridized one, like an sp3 orbital. All right? So this is a scenario of all sigma bonds. And then let's move on to talk about double bonds. So now using ethane, which is the C2H4 with a double bond in center. So here the logic is the same. We first count the steric number at the carbon center. And since the steric number equals to 3, what we're having is a sp2 hybridization. Or each of the carbon here are trigonal planar. And we have a double bond in between. So if you think about it, how do you understand the chemical bonds? For the carbon, each carbon, what we have here is sp2, 3 of them, and 1 lone p atomic orbitals. So that's for each of the carbon here. All right, if you put the electrons in there, they're all singly occupied. Again, sp2 coming from 1 s atomic orbital and 2 p atomic orbital. That's why you have 3 sp2 atomic orbitals. And now we're ready to make chemical bond here. What we're doing is we're just draw the carbon here. We'll draw the sp2 atomic orbitals first. I'll use the red color for your sp2 atomic orbitals. So you can have the sp2 interacting with the sp2. I'm just leaving out that small tail there. And then you have two more sp2 interacting with the hydrogen. One S. All right, so if we were to label these chemical bonds, this one is the sigma sp2, sp2. And here, the CH bond, that's our sigma sp2 and S of the hydrogen. So far we're happy. But what about the p orbital? We have one singly occupied p atomic orbital in your carbon still. So I'm using that green color to draw the p atomic orbital. So that's what your p atomic orbital looks like. By putting the two p atomic orbital close to each other, what we're creating is a pi bond. So this is a sigma bond. You have the atomic orbital pointing towards each other. And a pi bond is that these lobes are overlapping with each other to form that pi bond. So naturally, what we have here is the overlap of your p atomic orbital gives you a pi bond. All right, let me finish in one quick sentence. The other way to think about it is I always like to add a little cartoon. Is imagine this is a burger, right? That's where your carbon is. And at the end, we have some hydrogen, CH bond. We don't care that much. But if we're just focusing on the carbon-carbon bonds, what we have is in the center, that entire beef patty demonstrate that's your sp2-sp2 interaction to form that sigma bond. So that's in the middle. And then both of the breads here on the top are your pi bonds. All right, so not just the top one, it's both of the bread gives you the first pi bonds. Question?
For the pi bond, would that be non-bonding because it's not like...
No, that's a different concept. So we only use non-bonding for the MO theory. It's two different concepts. So the p atomic orbital here are singly occupied. They are making a chemical bond. They are making a pi bond. It's two different concepts. Don't mix them together. So whenever we're talking about non-bonding, we're just saying that atomic orbital is not interacting at all with anything. But here, the atomic orbital, the p atomic orbital of your carbon is interacting with another p atomic orbital of your carbon. So that makes a chemical bond. And this chemical bond is called a pi bond. Yes?
I'm going to ask, like, the one on top and the bottom would be like the px and py, right?
No. So the one on top and the bottom are all coming from one single pi bond. So both of them are part of your pi bond. We're talking about the product here, so we don't have any shading, not like what the model have. But both of them are part of your p atomic p interaction. So the top part is and the bottom part are both part of your p atomic orbital. When you put them together, both of them interacting with each other to form a pi bond. So both the top and bottom part are part of your pi bond. So that's one common misunderstanding I want to highlight here. All right, so both of your bread pad are your pi bonds. All right. So following up, let's look at the triple bond. Here for the triple bond, again, looking at your carbon center, we have steric number equals to 2, which means here the bond angle is about 180. And both of your carbon center are sp hybridized. So if we draw the energy level diagram, both of your carbon have the sp hybridized atomic orbital and 2 long p atomic orbitals. All right, remember you have 2 sp because it only contains 1 s and 1 p. And all of them are singly occupied, ready to make chemical bonds. So what does the chemical bond now look like? What we're thinking about is, again, let me just copy that down. All right, we're talking about the carbon sp hybridized atomic orbital interacting with another sp hybridized atomic orbital. One thing I want to note is we nearly always make sigma bond from hybridized atomic orbitals first. So the sigma bond coming from sp atomic orbitals. So that's my sigma sp sp. And also the sigma sp sp interacting with s of hydrogen. So that's sp s s. All right, so these are the sigma bonds. For each carbon, it uses one of its sp to make a sigma bond with a hydrogen s atomic orbital. It uses another of its sp to interact with its neighboring carbon to form that carbon-carbon sigma bond. And then we come to talk about the pi bonds. I'm going to use 2 different colors, the red one and also a green one. Imagine that carbon-carbon bond length, the carbon-carbon bond is my z atomic orbital. So what we have is z. Well, let me use a different color. So this is z. And then you can also have x, y. So 3 different directions, 3 different atomic orbitals that are perpendicular with each other. Right? We have 3 different ways these atomic orbitals can organize. So my px will interact to form my first pi bond. So everything in green here is all one single pi bond. I call it px. You can also call it py. I don't care how you call it. But at the same time, you also have another singly occupied p atomic orbital. So that's like this. Right, so everything in red here are my p, py, py. So everything in green is your first pi bond. Everything in red is your second pi bond. So if you think about it, this is a, let me use the same color. Yeah. All right, so if that's your first pair of your pi bond, you can have a second pair of the pi bonds coming in different direction. So these lobes are perpendicular to each other, but then both of them are valid. It's not perfect, so it's not. A second. All right, so if you think about it, this is the sigma bond we're talking about. And then these pair, the red ones, are my green pi bond that's vertically perpendicular to that sigma bond. But then in and out of the plane, there exists another pair of the pi bonds, which is my red ones. All right. So before I conclude for today, I'll post a extra credit assignment on Canvas. Some of you might already see it. Can you imagine a food item that actually resembles the triple bond? It's not going to be a burger, because the burger, you only have one layer of the bread. And if you think about it, the pi bonds are perpendicular to each other, so it's not a triple burger neither. So can you think about a food item or anything? You can ask ChatGPT to help you, but so far I haven't got any luck. So it's going to be posted on Canvas, and just think about it. What a pi bond, what a triple bond looks like if you have a food item to resemble it. Any questions before we conclude for today? Okay. The steric number tells you how many hybridized orbitals are there. Yeah. Okay, nevertheless, I'll stay here for questions if you have any. Hi.
Is hybridization going to be on the midterm?
Some of them will, because we discussed the fundamentals of hybridization, right?
Yeah.
But these parts will not be on midterm.
So, like now, are we given what the hybrid, like now, is hybridization linked to the geometry like that, right?
Right, so the steric number tells you what's the hybridization. So if the steric number equals to 2, you only have 2 hybridized atomic orbitals, so that's the sp hybridization. Right, but
SP3 or SP2?
Well, it depends on your steric number. If you have steric number equals to 4, then you have 4 hybridized atomic orbitals.
Of
sp2, that's 3 atomic orbitals. That's coming from steric number equals to 3.
Okay. I have more questions. Are you going to be available tomorrow?
What's that?
Are you going to be available anytime tomorrow?
I will be around tomorrow, yes and no. So tomorrow I have some other research-related meetings, so I'll be around, but I might not have time to have office hours. Because my Tuesday is always research.
Okay, but Wednesday?
Wednesday in the morning we have our midterm.
Yeah, but like, it's till 9.
Yes. Well, if you like, we can schedule sometime early Wednesday morning.
Okay,
anytime before 9 will be fair, because I can't answer question after the exam starts, right? But if you can stop by before 9 o'clock, we can talk.
Okay.
Yeah. And then you need to send me an email about when you want to stop by on Wednesday. Let me just grab my seat outside. Okay. So who has just a quick question before? Okay.